Thank you. Yeah, so I'm Philip Pessis. I'm product manager for NXP's automotive group covering the Americas. We're going to be talking about machine vision, algorithm development, and simulation using our NXP Vision toolbox for MATLAB on our S32V based processors. And my colleague Daniel Popo will take over in about 10-15 minutes to get the second half of the presentation. Okay, a little bit about the agenda. I'm going to do a little introduction about the vision processor called S32V. Then I'll talk about the enablement that goes with that processor. And then when I hand off to Daniel Popa, he'll go through the MathWorks ecosystem, the embedded development process, the NXP Vision toolbox around the processor, and then go through two demos, one on object and feature detection and the other on neural networking using SqueezeNet. So, an overview of, I guess, a view of our roadmap. This is our second generation of vision processors. Our newest family is called S32V 2, 3, 4, and then the 232. These are dual and quad core ARM A53 based processors. We've got multiple options available for customers, some with the graphic processor unit or the GPU, and some without. And then I'll have a little bit more detail on the processor itself. But where we're aiming this device and where we've been successful are primarily four different vision markets. One is on surround view, doing a bird's eye view or segmentation around a vehicle, and so that could be quad cameras, it could be 8 cameras for commercial sized vehicles. The other is driver monitoring, so that's why we have some facial detection and other algorithms that we've developed. Another is for sensor fusion, having a safety device that's capable up to ASIL B or ASIL C, which is what the S32V 234 is rated for, allows some additional redundancy in hardware to make safety critical decision making. And then the last is addressing the in-cap camera vision, forward backwards camera systems. And in the future we'll be looking at trying to do higher resolution, farther distance cameras supported by the V3 processor coming out, in the next year or two. So, a little on the block diagram for S32V234, we've got 4 ARM Cortex A53 cores running. We have options for 800 megahertz all the way up to 1 gigahertz per core. These can be put into clusters to reach that ASIL C level of safety performance. Altogether, there's about 10,000 DMIPS of performance through those cores. We also have an ARM Cortex M4 core that could also be used for redundancy or safety checking of different tasks. We, on the vision acceleration, we've got IP that we call Apex 2. These are vision accelerators, and we've got 2 of those modules, and these have 64 computational units per accelerator, and so you can use these to get really higher parallel processing on the vision extraction and data processing on the vision side. We've also got 2 different memory, or sorry, not memory, 2 different camera interfaces. We've got dual MIPI based camera inputs, as well as 2 parallel 16-bit input. We also have embedded an image signal processor, an ISP, for HDR, color mapping, and tone correction aspects. I did mention earlier we do have a 3D GPU also on ship. That's the GC3000 from Vivante. That's also on ship. And then we can do H.264 video encoder and decoder on the video side. In addition, we've got a lot of functional safety overhead built into this chip. So you see it down on the bottom right side there in gray. We've got fault control and collection unit. These lets you monitor faults and set flags and or take action when a certain parameter or certain fault is detected. We have built-in encryption security into the chip. We've got 4 meg of internal SRAM with ECC across all the different memory interfaces. And then we also have gigabit Ethernet support on chip. And this entire family is supported for 15 years of availability through our longevity program, and it supports minus 40 all the way up to 125 junction temperature. You know, on the S32V, you know, when you're handling the vision pipeline, you know, it starts with the inputs coming through the ISP, using the Apex accelerators to classify, you know, applied neural network or kernels, and then you could use the transformation or extraction and or safety task can be handed off to the ARM A53 cores, and then you can render or output that to the GPU. That's kind of our pipeline for the vision side. On the enablement side, we've got a free or no-cost Vision SDK or software development tool kit. We call it Vision SDK. We've got 50 different code examples built into this library. We've got neural network classifiers that are built in. We've got facial recognition, pedestrian detection, dual camera disparity. We've got a lot of things out there to help customers get started. And you know, we continue to build on these as we have moved through different development phases. We've added more capabilities. We've also got driver monitoring system coming that's going to be available here later this year. That's also going to be supported inside this processor family. So on the vision software development, we've got application partners. We've partnered with Newsoft and Hella Gaia that supports, you know, in-cap and pedestrian detection for 2020, lane keep assist, and other different aspects. We advise customers, you know, that are thinking about using our processor, you know, to work with you know, proven partners that have already developed some of the aspects and safety mechanisms that they will need to be in production in a shorter time to market. We've got other, you know, aspects of partners on the software side. We've got MTech Vision for the ISP side. We've got, you know, Green Hills Integrity for premium tool chains, QNX, and other. We've got many partners out there. Too many to name here, but you know, customers have help and support there in addition to what we're providing for free. So inside, you know, the support for the software inside NXP, we've got a free Vision SDK toolbox. We've got MATLAB Simulink models that are also free and available. We've got AutoSAR software, MCAL drivers and OS support, and we've got graph tools that we've GUI-based graph tools for the ISP development and the Apex Vision Accelerator development. And then on the hardware side, we've got an SBC S32V 234 hardware board that's about $649. That's already in stock at many distributors and e-tailers on the web now, as well as the NXP page has this board for sale. These are made up of 2 pieces. It's a carrier board that has your 2 MIPI, you know, camera inputs or deserializer inputs in all the different, you know, interfaces. And then there's a SOM board. That's where the S32V processor is on that SOM board, and then it has a passive heat sink on the bottom side. Currently we've got about 5 cameras currently supported. These range from the Sony S32V Sony camera. We've got 2 different OmniVision, or sorry, make that 3 different vision cameras. We got the 10640, the 10635. We just recently added additional support for the 9716 MIPI-based camera. That works with the Maxim deserializer that you see on the right side. And then we also support the AR140 recently, and that supports the TI SerDes adapter that you see on the right side. The two bottom cameras are available. We do have firmware and drivers to support customers that are using those cameras or deserializers. However, they are not currently bundled inside the Vision SDK that's downloadable today. So we'd have to work with you to get that software, I guess, offline. It doesn't come prepackaged in the software, but the support for the top three cameras are already embedded into the Vision SDK software. On the right side, you've got the Maxim deserializer that supports, 4 different LVDS camera inputs, and then you've got the TI UB964 that supports the OV10640 and the AR140 cameras, and it also has the 4 LVDS inputs. Okay, at this point, I'm going to hand it over to Daniel, and he'll walk you through all the math work and MATLAB demos.
Okay, thank you, Phil. So let me see how I can share. So
hey, Daniel, I just gave you the moderation rule. Perfect. Now we see the presentation. You're good to go.
So I'm going to start with a short introduction of the NXP Vision Toolbox to clarify what this tool is and what kind of application it's suitable for. And then we are going to see how we can tackle advanced driver assistance systems application using NXP solutions in conjunction with MATLAB ecosystem to create, simulate, and deploy computer vision and deep learning application on S32V ARM-based automotive-grade processor, and also to benefits of the dedicated hardware accelerator which are present in this platform, as Phil just mentioned. So let's see what kind of problem you can address with such tools. For the beginning, we are going to start with a typical use case for ADAS, where you can group various tasks related with machine vision in 3 categories: sense, think, and ultimately the acting part. The sensing part is handling the environment perception. Here is where our toolbox plays a major role because using our toolbox built-in capabilities, the users can perform various tasks related with object detection and also feature extraction that are accelerated using ARM or Apex cores. Once the various objects and features from camera snapshot are detected, then we need to think about what those objects are in respect with the type of application we are trying to build. We might need to employ various modeling techniques like classifiers or tracking algorithm to figure out how these objects are interacted with the surrounding. It is not enough just to identify the objects, but it's also important to know where you are and map this information against those kind of objects. So you need some sort of local maps, sensor fusion, localization, all this kind of things that need to be put in perspective. And once all these informations are available, and the data processing techniques are done, then you need to act upon of those information and plan for a free path to avoid possible incidents by taking informed decisions. So as you can see, all these steps can be done completely in a environment, a software environment like MATLAB. And for the next slides, let's have a look and see how this MATLAB can help you with reaching all these actions. So to address the complexity of ADAS system, besides hardware and runtime software, we also need to consider the development tools. In this area, we are recognizing the added value of the MATWork solutions and decided to offer our customers the option to develop applications directly from MATLAB for a multiple embedded platform that can be found under NXP product portfolio. So if we consider as an example a typical modern car when we need to deal with various software development challenges that need to cover for a multiple of functions, let's say from common ones like vehicle dynamics and body controllers up to more complex tasks as sensing the surrounding using radar or camera, then it makes sense to have a unified tools ecosystem. In case of machine vision and artificial intelligence, MATLAB is offering a good selection of various toolboxes that can speed up the software development by offering the means to process the camera snapshot and enhance the images with various dedicated image processing techniques, and then run complex algorithm to identify the object and context within each image. Once the objects are identified and labeled, then we can run driving scenarios to check if the controller reacts to various stimuli and if it reacts correctly. And the beauty of all of this is that we can do it in a completely safe simulation environment. So we don't need to go out on the streets and test our algorithm. We can do it in a labs or on our desk to see how it behaves. So one may ask why MATLAB and not other tools like Python, for example, right? So there is no easy nor a final answer to these questions, but nonetheless, when evaluating such solutions, we need to consider the customers that needs to go from idea to a product. So commonly you go through this project phases like design, prototyping, test, and ultimately the deployment. And typically those stages are done in this particular order. And at each stage you update the original design based on your findings. So when you do this kind of updates, you do this kind of back and forward between those stages, and that may be a time consuming. You will need to update your documentation. You need to update your test cases and so on and so forth. With a MATLAB-based development process, we go through design, prototype, and deploy. So you may ask what happened with the test phase. Well, we continuously test our phases in continuously. So each phase it's continuously tested, and the findings are integrated in that phase over and over again. So the main idea with this approach is that you maintain a golden model or a golden reference in MATLAB, and having a single reference make it much more easy to make changes as the requirements change. You can get to test it more systematically, and you also take into account for more real-world scenarios. Additionally, you may integrate your design through the process, which you get from the idea to the product even faster. When I'm talking about integration, I mean you can reuse existing verified code and integrate that code into your MATLAB designs, integrate your design with existing prototyping hardware, and you can also deploy your algorithm into other software frameworks or legacy project with the C code generation. So all of those things can be done easily from MATLAB. MATLAB, especially the tools for automotive, were specially created to handle this kind of scenarios. So let's talk a little bit about how you do the things in MATLAB, how you can simulate, how you can test, and generate the C code, and ultimately deploy this kind of things on the real hardware. Within a typical ADAS system, we can find the various computing domain. We can find the vision part, we can find radar, also the application processor where we do the central processing. This sensing domain may be seen as a completely decoupled. Yes, you can see it independently. Or you can consider a bigger picture when all these sensors are just another way of seeing the world around us, right? You can see it with the vision, or you can see the radar images, right? So in the end, it's is the way you sense the surrounding. And if we assume this true, like it's just another way of seeing the world, then it also makes sense to tackle the programming of this domain in a unified way. And this is where MATLAB-based toolboxes offers a lot of advantages, right? So once you get familiar with vision, then you can easily move in the same, let's say, environment and tackle the radar part, or even the application part can be tackled with MATLAB as well. For each computing domains, there are dedicated toolboxes that works in both simulation and real target code generation, so that the development flow, it's let's say overall simplified. You don't have to handle with separate tool chains. In terms of perception, we are using computer vision toolbox to enhance the snapshots from the camera. And then we are going to run complex algorithms supported by deep learning, for example, to detect and recognize such objects. Other toolboxes like advanced driving systems allow us to fuse the data from multiple sensors and track this object in respect with our position to check if they represent a potential threat. Once the conditions are known, then we can act upon and decide what is the best, let's say, avoidance path of the car. But in the end, the foundation of all this toolbox or all these tools, enablement from MATWork, is represented by NXP Vision Toolbox, which is used to close the gap between MATLAB, the MATLAB environment, and the NXP embedded target. So this kind of tools which we showcase today, it's doing this kind of final link and expose the NXP hardware into the world of MATLAB and Simulink, allowing the customers to take the benefits of dedicated functionalities in MATLAB, generate the code and test it on NXP target as well. So in order to support the machine vision development directly from MATLAB environment and to interact with various toolboxes that support image processing, computer vision, code generation, simulation, and so on, NXP is offering this vision toolbox, which is fully integrated with MATWorks product. And allow you to start by simulating the algorithm using MATLAB functions, or maybe NXP Max wrappers, which are built on top of the Vision SDK that Phil mentioned earlier. And based on those MATLAB M script, you can generate the embedded code, and deploy it to the S32V microprocessor. Once the setup is configured, and I'm talking here about cross-compiler for ARM or for Vision Accelerator, SD card, Linux images, board support packages, and so on, the entire software development can be done using only the MATLAB environment. So you don't leave the MATLAB, you do everything in MATLAB, simulation, code deployment, everything, and you will see throughout the demos how we can reach to this level of let's say integration. So to help the user in setting up the environment for software and the hardware, because you can see that there are a lot of links that needs to be addressed here, the runtime software for the ARM, the NXP Vision SDK, cross compilers, and so on. We are offering an option, it's called NXP Support Package add-ons that can be installed directly from the MathWorks website. And these add-ons can guide you through various steps where you can make sure your installation is completely and it is also correct, right? So in case you are interested, this toolbox, it's available for download directly from MathWorks website. Now let's have a quick overview of the typical development flow that involves the NXP Vision toolbox before going to the demo itself. So as mentioned before, it all starts with MATLAB, right, on the PC side, where you can begin by playing around with ideas and implement algorithms in a simulation environment. The simulation can be done in 2 steps. It can be done with, let's say, built-in MATLAB functions, right, from computer vision system. Probably some of you are already familiar with that. And the second option is to use the Max wrappers that are built on the Vision SDK libraries, which are provided by NXP. So with the Vision Toolbox, you also get the MATLAB models of the C code, which is implemented in the Vision SDK, and you can play with the same functionalities that ultimately will run on the target itself. In this way, you will have a one-to-one, let's say, bit exact comparison with what is done in simulation versus what is done on the real hardware. Once the simulation is completed, the MATLAB coder, right, this requires an additional license from MathWorks, can be invoked to translate the M code, the M files, into the C or C++ code that needs to be run it on the target. At this level, you have 2 options. You can continue with our build toolchain and deploy the code directly to the ARM cores or Apex core, depending on what kind of functionality you have used to implement the M programs, the M files programs. Or you can stop at this level, get the generated code, integrate it into, let's say, another development environment like S32 Design Studio for Vision IDE, get some legacy code as well, and then download it via JTAG to the ARM cores as well. So at this point, you can split, you can decide whatever you do with the generated code. Typically, in the next demo, we are going to show the direct path where MATLAB can handle the cross-compilation of the files and also the deployment via the Ethernet to the ARM and the Apex core, to the accelerator itself. So let's see how this flows maps over a basic object and feature detection application. I'm going to demonstrate how to create a small program that works under MATLAB simulation using video frames from S32V microprocessor, ISP camera. It's a Sony camera. So basically, you will see how you can use our NXP hardware as a, let's say, as a webcam, and then how you can deploy that program on the real target using our Vision Toolbox built-in capabilities. The demo itself, it's focused on the face and face feature detection. And you can consider it as a basis for a more complex driver monitoring system, right? It is not a complete application. It's just to give you a, let's say, an idea how the things are done in terms of software development with this kind of tools. Our purpose is not to, let's say, to provide the final application here. So as a first task, we need to detect the faces within each video frame that we take from the camera. And the easiest way to do that is to use local binary patterns, the LBP or the HAAR algorithm. So these are the most, let's say, common algorithm that you can use for face detection, for example. This algorithm detects object in images by sliding a window over the image itself, and then the detector uses a cascade classifier to decide whether the window contains the object of interest. The size of the windows may vary, right? It may be scale in order to detect multiple objects of different scales. But when you do this, you have to consider that the aspect ratio remains the same, right? That the features are defined in a fixed way. The detector is very sensitive to out-of-plane rotation. So if the face is rotated one way or another, it may not trigger because the aspect ratio changes for the most 3D objects, right? So therefore, you need to train the detector for each of this orientation of the object. The basic methodology for LBP when is used for face description is as follows. So the facial images is divided in 9 regions. And for each of these regions, we extract LBP texture descriptor, right? So it describes some information that characterize that type of region. And then all those descriptors are concatenated to form a global description of the face. So you can think about this kind of rectangular. They have some weight, and it is a numerical way of describing the face, right? So local binary patterns, it's simple, yet is very efficient, and due to its discriminative power of computation simplicity, the LBP has become a popular approach in various applications. Perhaps the most important property of the LBP in real-world application, it is robustness to monotonic grayscale changes caused, for example, by illumination variation, the kind of things you have seen in the first presentation of today. Another important property is the computation simplicity, which make it possible to analyze images in, let's say, a very challenging time, real-time application, right? So it's quite fast, and it's very suitable for the embedded application and for hardware accelerator. To detect the features, we are going to use the HAAR algorithms. So the HAAR algorithm considers a side-by-side rectangular at a specific location in the detection window. It sums up all the pixel intensity for each region and then calculates the difference between this sum. The difference is then categorized to say what that image is. For example, let's say we have an image database with human faces, and I think we all agree that it's a common observation that among all the faces in the region of the in that region of the face, the eyes are darker than the region of the cheeks, for example, right? So therefore, a common HAAR feature for the face detection is the set of 2 rectangles that lies above the eyes and the cheeks region, and based on this kind of properties, we can identify whether or not we have eyes, we have mouth, we have nose, and so on. So this is another way of extracting the features. The key advantage of the HAAR feature over the most or other features like neural networks and so on is the speed of calculation. So using this HAAR-like feature detection, we can compute it very fast. It takes about 60 processor instruction, right? For if we consider this kind of 2 rectangle approach, right? If you get more rectangle, 3 rectangles, for example, it may take longer to identify, but it's good enough for the things we want to do. Also, to eliminate the false detection and to reduce the area for searching various features related to the human faces, we are going to employ the Kalman filter. The Kalman filter is an algorithm that uses a series of measurements that are observed over the time. Those kind of measurements may contain statistical noise and other inaccuracies, and produce an estimate of the unknown variables. So the filter itself produces the estimates of unknown variables that tends to be more accurate than those that were obtained from the single measurement. So using this kind of Kalman filter, we can eliminate false detection, and we can focus only on the human face to extract additional features. We call this like a region of interest. The algorithm works in 2 steps. There is a prediction steps in which the Kalman filter uses the previous states and the model to predict the current one. And it's another correction step at the end that the filter uses the current observation to correct the predicting state. So it is a recursive algorithm that is doing this all the time with the data that we feed in. So we can force the model to have more trust in the model by decreasing the variance in the Q matrix. Likewise, we can force the filter to have more trust in observation by decreasing the variances in the R matrix. So for this demo that I'm going to show in a few seconds, we train these matrices, or we choose the weight of those matrices empirically. We just run it through some videos and see how fast the Kalman filter were able to track the faces moving. And depending on that settings, we adapted the weight of those matrices. So this is the actual the actual code, right? You can see that the first step is to create an object to connect it with the NXP S32V from MATLAB. This is done with the dedicated functionalities here. Then we need to initialize the LBP and also the HAAR detectors. And ultimately, we need also to initialize the Kalman filter. And then we go in an infinite loop where we take the images from the camera, and at each step, at each frame, we are going to run the face detector. We are going to filter those detections, and then we are going to extract the features of that face. In particular, we are looking for the eyes. And of course, the last step is to display the let's say the results and see it on the screen itself. So let's see how this works. I have prepared a short video here. I hope you can see it. It's a low resolution, but so it is the same example. It's a little bit enhanced. It is enhanced by allowing you to run it in both simulation and the hardware, but you can see the same critical aspects here, connecting to the target, taking the frames, initialize the detectors, and also going into this infinite loop where we can add different information like how fast we process the things, and at the end we put the results on the screen whether or not the feature is detected. The algorithm can also work with other of the features like eye, like mouth, nose, ears, and so on. So to run in the simulation is very easily. You just simply run it on the MATLAB. Now it's connected to the target, as you can see, and is going to display on the MATLAB figures what the camera is seeing, and is going to run the algorithm. You see my colleague here is moving from one side to the other in order to show that the Kalman filter is doing its job, right? It's tracking the face very well and also detect the eyes itself. So at this point, we have identified the objects. Now it's a matter of saying something. Think about this. So what that information means, right? So a typical approach here would be to use the convolutional neural network to predict what happened on those frame, right? So you can think of an example like, is the driver tired? Is the driver distracted? So on and so forth, right? So all this kind of analysis can be done with an AI, an artificial intelligence, in this case, a deep learning type of algorithm. So let's go a little bit and see how you can do this kind of artificial intelligence or deep learning with the MATLAB. MATLAB also provides a lot of, let's say, convolutional networks. They are especially suitable for images as an input, but they can also be used for other applications such as text, signals, and why not any other continuously, let's say, response-based application, something that happens in real time and you need to monitor. To speed up the development, you can take a pre-trained classification network. So these are the networks which are, let's say, supported by default in MATLAB. Oh, sorry. Using this plot, what you can see here, we can compare using the ImageNet database, the accuracy for network and the time requires to make a prediction using this kind of images from the ImageNet database. The plot that you see here display the accuracy, the classification accuracy versus the prediction time, right? So I just want to point it that you see this kind of dotted line here. This is the Pareto efficiency line, and it is defined like the point where there is no other network that is better on all the metrics being compared. So in this case, the accuracy and the prediction time. So if we take it, let's say from the beginning, like you see here the SqueezeNet, and you also see the AlexNet. All right. So the SqueezeNet in this case, if we consider the accuracy and the time needed for computation, it's better. It is just on the line of Pareto frontier because it takes let's say less time for processing than an AlexNet, and it's producing better results in that condition than AlexNet. So for this example, we choose the SqueezeNet. One of the reasons of choosing this SqueezeNet is its let's say size and the number of parameters. You see it's the smallest of the all, and it fits very well within let's say our embedded systems. So this is the SqueezeNet network which are using for this demo. In this particular net, this convolutional neural network is trained on more than 1 million images from the ImageNet database, and it consists of multiple layers such as convolutional layers, max pooling or average pooling layers, and also fully connected layers. So the network in this case is 68 layers deep, and it can classify images in about 1,000 object categories, such, let's say, keyboard, coffee mugs, cars, planes, whatever, right? The implementation from MATLAB is based on version 1.1. which has a similar accuracy to SqueezeNet version 1.0, but it requires fewer floating point operation per prediction. And also, we need to consider that the input in this network, it's a 227 by 227 image. So we need to scale the image down from the camera in order to pass it to the network itself. So this is the example which we are using. It's 25 lines of code. Again, you can see that we are going to connect to the target. We are going to initialize the camera. The camera has a larger native resolution. And then we are going in an infinite loop, take a snapshot from the camera, resize it, call the SqueezeNet, right, network to classify the objects, get the object ID and the percentage of accuracy, how well he found the object, and then we are going to plot those results on the screen. So let's see how it works. Again, this is the example itself, the same steps. So this program works the same in simulation and the hardware itself. You can see here a little bit more details about what we are going to do. Just for simplicity, so this is the SqueezeNet. We are using the default function from MathWorks, right? And we are going to plot on the screen the 5 best fitted answers from this network. So you see now I'm running on the simulation environment. It's connecting with the board, right? And now maybe you don't see very well the numbers here, but if we change it in let's say in real time and feed it with different objects in front of the camera, the neural network can predict quite well what that object is, right? So you do this first in simulation. You make sure the things are running in simulation and you get the good results, and then you can move to the target itself. To move to the target, it's quite easy. You just have to generate the network itself using a script like this, where you just call the code generation. And similar with the previous examples, this code is then also linked with additional source file, additional libraries from the Vision SDK, and you can run it on the target itself. You see here, this demo is running on the SBC board that Phil showed to you, $650 board, and is producing the correct example. So please consider that this network was just took from MATLAB. We haven't done anything on it. We didn't fine tune it. We didn't train it. We didn't do anything. We just deploy it on S32V processor, right? And just out of the box, it's providing, let's say, some good enough prediction. Like you see, it can detect a banana with 96% accuracy, right? So what you can do with this kind of application? Well, using the pre-trained network with transfer learning, it's typically much faster and easier than training a network from scratch, right? You don't have to spend too much time investing in that. And if you really want it, you can fine-tune these deeper layers also directly from MATLAB. So MATLAB provides you all the additional tool set to do these things automatically. And once you are satisfied with the results, you can deploy it on the real hardware, right? Using our Vision Toolbox, which allows you to link the generated code with the additional libraries and runtime software needed for the Vision SDK. And finally, I think it worth to mention that you can import networks and network architecture between or from TensorFlow, Caffe, or other the frameworks like that, using the Open Neural Network Exchange model format. And why not? You can also export, if you are satisfied with the results in MATLAB, you can also export those to other framework that you may want to use in your production environment. Right. So very quickly, I think these are all the information I want to share with you for today. Just to go over the conclusion, I think for the most efficient development, remember that we say in the beginning that we need to go from idea to product quite fast. We can combine, you should consider combining the MATLAB and MATLAB coder, because this gives you additional advantages like generating an ISO 26262 code, or I don't know, compliant with different standard codes and so on. You don't have to pay attention, or you don't have to invest too much time in making sure your code is compliant. All these kind of things are done by MathWorks product, and the only thing you have to focus is to refine the algorithm itself, right? Therefore, you spend much less time writing and debugging low-level C code, and you spend more time developing and tuning your algorithms. And in case you are interested for more information about NXP solution, you can visit our dedicated online community where we can answer to your questions here. Or I don't know, if you are interested in evaluating the NXP Vision Toolbox, you can find this web page where you can get a good starting point for resourcing, documentation, updates, and so on. So thank you for your time. This is all I had for today. I hope you found it interesting, and if you have questions, I'm open to any of them.
Thank you, Daniel and Phil, to both of you for this presentation. There actually are a few questions I would read out for you, and maybe you can give a brief answer on that. The first one would be, is it possible to collect and analyze data from the S32V camera in MATLAB? Is that possible?
Yes. I think I just showed you can connect it very easily. It is a dedicated function that our toolbox exposes, right? And you can get the frames from the camera directly on your MATLAB. So if you are planning to use this kind of high-level algorithm and drive the car on the street and see, you know, in real time how your algorithm may behave, you can stream those data directly into the MATLAB and you know, and analyze what the car it's seeing.
And a second question is, can I run native MATLAB code on the S32V without calling the NXP wrappers and classes?
Yes, I think the last demo, it's just that. So we run the native MATLAB code as a, let's say, deep learning. The only problem with this approach is like you run it only on the ARM cores, so you don't take the benefits of having the hardware accelerator as the apex, right? So overall, your application would be a little bit slower, but this is why we build these wrappers and special functions on top of the Vision SDK, because Vision SDK is providing kernels which are optimized for speed and accuracy. And if you are going to use this this functionality in MATLAB, that code, instead of going on the ARM and execute it on the ARM, it will be deployed on the Apex accelerator. So you get an increase of performance very fast by using our kernels. And all these kernels in general are OpenCV-like, so quite the same parameters. So it's easy to adapt your program to use NXP wrappers instead of MATLAB built-in functions.
Good. Then I can read out the next question. How did you train the objects and features detector?
I think I think I mentioned, but we didn't train anything. So we took a pre-trained network from MATLAB, right? We took it as a pre-train and we use it as is. I think Phil can comment here. He might know better than me. But NXP is also providing, let's say, an AI runner. It's a tool that can help you to, yeah. So,
yeah, just a quick question. So we've developed a machine learning. I'll call it an add-on to our Vision SDK platform that it's still in alpha stage right now, and we're working on making a broader release inside the Vision SDK download by the end of the year. So there'll be a framework built inside the free software.
Okay. Then I will just move on to the next question, which is also maybe slightly related to that. Somebody has the MATLAB 2018B with image processing toolbox and also wants to know about the integration with NXP hardware work within this version of MATLAB and the toolbox. Is that something you could answer?
So when we I think in one of the slides I showed that our toolbox, our NXP Vision toolbox is making the last link available between the MATLAB and let me go to the slide. Yeah, here. So whatever you have in MATLAB, even if it's 2018A or B or whatever, you probably want to use 2018 version because it's more capable in terms of code generation and the speed of the executed code, right? But in order to enable computer vision, for example, you need our, let's say, toolbox as a baseline in order to connect to the target. Once you bring the data into the MATLAB environment using the, let's say, the camera object, right, then you can do whatever you want in computer vision. If you just use computer vision as is, right, without any additional NXP wrappers, then that code you have to consider that goes on the ARM cores itself, right? So it runs as fast as the ARM core can do, right? It's a 1 gigahertz processor. It can do some performance, right? But you can also enhance the functionalities from computer vision with additional wrappers from NXP, and you get the benefits of running faster. So we can run, for example, face detection about 30 frames per second just with generated C code, right? Nothing handwritten. I hope I answered the question.
Thank you. Then the next question is, what is the difference between computer vision and the deep learning toolbox? It's a common understanding that the deep learning is slowly replacing computer vision. In this context, what is the difference between both and when should we use which one?
So typically computer vision, it's dedicated more on the, let's say, raw functionalities for the images. Like you can apply different filters, you can apply different heuristics that can extract, let's say, different, let's say, information from the frame itself. So it's a tool that it can work on the images itself and gives you the raw information, right? When you talk about deep learning, you have to be focused more on the artificial intelligence and what you can do. So basically the deep learning in the end needs some inputs from computer vision because the deep learning doesn't have all the functionality of computer vision system. So he doesn't know how to, let's say, to handle all the images, right? If you want to speed up the development, you may want to add different filters and so on, which are not available in the deep learning itself.
Thank you. Then I think we can move on to the next question, which is we want to make a proof of concept for collision detection by detecting license plates. How many images do we need of license plates to train a model to detect the license plates?
I think we can go to the final stuff here. So we are, let's say, we are not, or at least I'm not an expert in this area, right? But what I can suggest is like you take a pre-trained network, which is already learned to classify images, right? And then using the transfer learning, you can feed additional images. I don't know, a couple of hundreds or tens of thousands, whatever, right? As many as you have, right? And fine tune the last layers in the network, right? The ones that are capable to identify the license plates. Right. I think this is something that you can easily do in MATLAB. They provide all these kind of tools to do this transfer learning, right? And it can save a lot of time. Just consider that the original SqueezeNet in MATLAB was trained in millions of images from ImageNet database, right? So you can get rid of that time of learning just by fine-tuning the last layer in the network, depending on the network you are choosing. But my general suggestion is like start with a pre-trained network, see what it detects. If you are not satisfied with the results, then you have two options: replace the final layers to match your, let's say, your desire, or just feed additional information to the layer to the network to classify that specific use case with higher accuracy. Typically, this is how it's done in the industry. I hope it's the answer you expect.
I'm sure. Thank you for answering that as well. Maybe one last question. Can we get application image which can be run on board directly? It's a question that refers to how to know the. Can we get application image which can be run on board directly, i.e. to know the HW capabilities and to review without starting development?
Okay, so there are two things here you can do. So if you are interested in evaluating just the hardware itself, the S32V, I think Phil just mentioned a slide before where you can take about 40 examples, right, from car detection, human pedestrian, and so on and so forth, that you can run out of the box on the hardware itself and evaluate what's going on. Also, our toolbox, which is delivered as a MATLAB one, comes with a couple of applications. We have face detectors, we have a pedestrian detection, we also have lane detection application that can be run as is from MATLAB to the S32V. But also keep in mind that you can also take a lot of examples from MathWorks website, typical for computer vision systems, that you can also run it on the hardware itself. The last demo which I showed, the CNN demo with the SqueezeNet, is just that. We just took the example from the MathWorks website and we run it on our hardware. Right. So you have three options here. Probably you want to go first with the examples from Vision SDK, because I think they are provided already built in, and it's just a matter of running the executable file let's say on the Linux environment on the hardware itself. Then if you have a MATLAB licenses and so on, the MATLAB environment, you can use the Vision Toolbox examples, which are built on top of the Vision SDK. And further on, you can refine even more and see what are the typical applications from MathWorks, which are developed by other guys, can work on NXP hardware as well.
And Daniel, can you make a comment on where they would find the image or the code image that you shared today?
So this all this will be our part, or will be part of let's say the demo libraries inside the Vision toolbox. So all the demos we have, we delivered, we ship it with the toolbox itself, similar with what Vision SDK is doing as well.
Is that do they link to that from the model-based design site?
Yes.
Or from the S32V webpage?
So they are interlinked. So everything on NXP website is interlinked. If you search for S32V, you'll probably also find the Vision toolbox as well, listed in the available software for downloads. So it's I think it's quite easy. Otherwise, in case any user runs into problem, my advice is to go on the community, put a question there. We usually answer within 24 hours, and we can provide additional guidance.
Yeah, and I don't know if I mentioned this earlier. I'll go ahead and make the comment now, but we've talked a lot about the Vision SDK software, as well as the toolbox. And the Vision SDK libraries are embedded inside of the S32 Design Studio IDE. So everything you need is kind of on inside one download, and that can be accessed either by going to nxp.com/S32V. And clicking on the software tab, or going to nxp.com/S32DS for Design Studio.